I'm sitting here in the boring room. It's just another race in the afternoon. I'm wasting my time, I got nothing to do. I'm hanging around, I'm waiting for you, but nothing ever happens. And I wonder. I'm driving around in my car. I'm driving too fast, I'm driving too far. I'd like to change my point of view. I feel so lonely, I'm waiting for you, but nothing ever happens. And I wonder how, I wonder why. Yesterday you told me about the blue, blue sky, and all that I can see is just a yellow lemon tree.
Hi everybody, how are you? Today we have an awesome tutorial about potential. And I know that most of the students are usually feeling a little bit confused about electric potential and don't have the intuition. And I found it really easy when you go back to the basics and talk a little bit about Physics 1. So what I actually did here, I built a battery. So today, the class about today is about electricity and its energy, potential energy. So what I actually did here is a lemon battery, and if you want, there's a guy that tried to actually engine his car using lemons only. Super cool video, find it on YouTube. And we actually made a really bad battery, okay? But this is a battery, and the way we measure energy is by this device, which is called Fluke. And if you remember Physics 1, how we measure energy, potential energy, was by height, and we're going to talk about that. So I actually can open the Fluke, I can see what are the point I'm starting, the point I'm ending, and I want to do the energy. So the energy here is around 0 point something. Let's go to the millivolt. Really weak energy. But if I'm going to take a battery, I'm going to measure this one. I'm going to have the value 1.5 volt, right, for this one. You're familiar with this. And let's explain what's happened to the lemon. I'm going to the board. So, we actually, when we have a lemon, going to this one, when we have a lemon, so it's actually act as a battery. This is a battery. You have the positive terminal, this one, which means high energy, and you have this one, the N, which is the negative, and this one connected to a circuit, right? Let's put a lamp here. Oh, and it's connected here, and go to the battery. So what's happening inside the battery? So in this side, we're putting a plate. We put, for example, zinc. And zinc have a lot of electrons. And the other side, we put copper. That's why I have these two little guys. I put zinc and copper, zinc and copper, okay? And the copper would really like to have some electron. It's like missing for electron. She wants the electron, but they cannot reach to the copper unless I put some juice, some lemon juice. And the lemon juice is actually making like a way for the electron to gain momentum and continue to the copper, and then actually electron can move inside the circle, which electron is the charge. The charge is going here inside the battery and actually light the room. That's the idea, okay? So this is actually gonna be the next subject, right? But we're actually gonna talk today about this mechanism, how we produce energy. That's the idea, this is the motivation. So, before we're gonna jump into energy, I want to do a small reminder, what is a work function? Remember, what is a work? What is doing your work? Okay, go to the gym and doing work. What is actually the term? So, if I want to calculate the work, it's equal to what? Do you remember?
Minus the integral of the force.
Right, but in concept. The concept is final energy minus initial energy. What is the change in the energy? Okay?
For conservative force only.
Huh?
But only if the force is conservative.
Yes, okay? Final minus initial, okay? If it's not conservative, some have lost, some is not in the picture, but this is actually the word. And you notice that we use U instead of E for energy. Why? Because E is already taken, it's an electric field. So we're going to use U. And this one equal to what? Somebody in the audience then get the credit, told us, wait, I remember it's doing an integral. Which integral? Integral on a line, on some trajectory, okay? On a line. So it's a 1D integral kind of thing. And multiply, you have here the force. What is this force? It's the force that I'm doing. For example, I'm lifting this, okay? I'm going to do it. So let's call it rho for simplicity to understand. The force that I'm doing, dot dl. And you remember dot dl? Remember what dot is doing? Killing the vectors, right? That's the idea. Okay? So let's look at three simple physics 1 question. For first of all, we can look at, I want to push this mass. For example, a week ago, a friend of mine got stuck at the beach and we need to push his car outside of the sand. So we have here a really hard sand to deal with. And after that, when we got to the road, it was really nice friction surface that we need to push to get to the road. So this is problem 1. Another problem which you're familiar with is stairs. For example, we're here in the international group, we have a lot of Chinese, so you have a lot of high places, a lot of crazy temples, mountains, you need to step a lot of steps, right? So stairs. So if this is me, I want to climb up and gain more energy, right? To be at that position. Another problem, and the most important problem is if I have here some charge, let's say Q, and this Q is actually what? Producing electric field, right? To all direction. And I come with my charge, this is my charge, for example I have in my pocket charge, I have some object with this charge, and I try to get closer to this would apply forcibly, agreed? And resist me. Here I have, let's talk about the forces. Here I have mg, right? Here I have some friction, right? And here I have some electric force, Coulomb force that will try to repel me, right? Perfect. So to deal with this, let's first of all deal with dl. Who is dl? Should be a small movement. Let's do dl, small. The camera see me?
Yeah.
Small movement. Okay? For example, in this problem, I can state that this one is the x direction. So actually moving this a little step, right? So dl equal to dx and the x direction, right? What's going on here? I can say that this is y initial and this is y final, and I want to climb in this direction, right? So dl equal to what? Y. Yes, sorry, dy. Right, that's there. And now we'll go to this problem, and we know that the electric field is radially, okay, it's producing electric field radially, right? So a small movement from here to here can be called dl equal dr, right? Simple. Now we want to deal with the other term, okay? To solve this, we deal with this dl, which we also deal with the line. We decide about some line, right? dl. And now we need to clarify what is this force in every one of them. Maybe I have a purple color. Purple, I love purple, yes. So let's do it with purple. So here, I am pushing, right? This is F1. I am pushing this mass. So F1 vector equal to minus this one. If I do it with no acceleration, right? We push it. So minus F, right? Vector. And what is this minus F vector is? Is minus mu n at the minus x direction, right? This is the vector, so in general this is equal to plus mu n x direction. That's what I'm going to do, right? What's going on here? I try to take myself, sorry, Ron. I try to take this guy and put it in this location, right? So I need to lift it. First resist me, mg. So this is equal to what? To minus mg, right? G is a vector. I can put g, the constant g, and have minus in the y direction. And then finally I have the magnitude mg in the y direction. Right? This is the first. Now the most important example. I'm going to this, okay? I'm going to this, and I said, okay, I want to push this charge into it. So this force actually equal to minus F electric, right? And using Coulomb law, we know what this size is. If we know the electric field, we can say it's a minus Q, with Q is the charge that trying to move around, right? And multiplied by some electric field, specific electric field. The electric field in space that try to move me, this one, not this one, this one. So this is Q actually applying on this Q, right? Agreed? Understand? Perfect. Good. So, so we have the force. Now we can do what? Solve the integral, right? We have everything we need in this table, right? All the cases. Let's go to this board. Sorry for, did you take a picture? Good, okay. So let's solve the integral for each case and learn some basic tools that we're gonna need later on. So the integral, what is the work? This is the question actually. What is the work for each case? So for the first case, the integral is what? Is the integral on the force, which is mu n. And I would just want to remind you, if I have the same signs, what's going to happen? Let's do a quick reminder here. Let's do it on red, because the is the red. So if I have this smiley normal direction, dot another normal direction, it's equal to the size of the normal direction square multiplied by cosines 0. By 0 because the two pointing the same, it's the same smiley, okay, it's the same object. So this is 1, this is 1, so it's just cancel out and we stay with the magnitude, right? So we have mu n dx, right? And let me just clarify, camera please, let me just clarify that. So let's call this one x initial, this x middle, when I change from sand to the road, and this is the end position. I want to put the car, the mass, okay? So, and I have two different mu, you see it? So what I can do to solve this, I can split the integral because I have two different mu. Mu is a function of x, right? So I can do from x0, x initial, sorry, to xn, we have mu1, which is the mu of the sand, plus integral of mu2, the camera with me?
Yeah.
Camera with me?
It's good.
Okay, good. And 2 because I'm moving to that side, dx. Okay, and this one from xm to x final. Agreed? Understood? Wonderful. So what is the next? The next problem? The next problem is actually to do the integral of mg dy, right? From y initial to y final, right?
Mm-hmm.
So I want you to see something really interesting that's happening here. First of all, I can say that this y initial is usually what?
0.
0. I can do it. Okay? I can decide that this is gonna be my realm. Start from 0 and ending at h. This is the convention, right? That's what people do. So what else I can do? M is usually constant. It's not always the case. If I'm taking, I don't know, this, mass doesn't change. A person mass doesn't change, right? But if I'm gonna take a rocket, it could change. It can lose fuel, right? So it's not always the case, but mostly is the case, right? So it's M, and G,
Constant all the time.
it's not constant all the time, but on physics 1, most of the time, it was a constant. Why? Because G equal to what? It's similar to Coulomb's law. You have G, big G, capital G, like remind the K. You have you have m of Earth, and you have the distance between you and the center of Earth, and it's usually on physics 1, it's get the assumption that this is the radius of Earth, right? Some 4,000 kilometers, I don't know, something big, okay? So if I'm here or on the table, dude, it's 4,000 kilometers. So if you remember previous tutorial, it's not a perfect wire, but it's such a good approximation. So this value is always 2.8, right? Most of the time, okay? So actually, all of this can go out, the integral. So it's mg, the integral from 0 to h of dy. So do you remember this term? mgh, right? This is usually what's happening in physics 1. Let's talk about physics 2, okay? Physics 2. Let's talking about this example, which is the most interesting one. And so I'm gonna clean this board, this part. I'm here. So what we actually have the work is equal to the integral of let's do it proper one. Let's say u final minus y initial equal to the integral of minus q, right? E q on q dr, right? This is what we have. Agreed? Perfect. So this is a constant, and it's from I don't know, r initial to r final. This is going to be r initial. Okay? Some distance r initial, r final. Agreed? Q is
Constant.
most of the time constant. It could be, for example, I'm research the lungs, and how we can make more drug delivery to the lungs. So if I inhale some aerosols, a medicine, which a little bit charged, so the charge can actually a little bit go away by humidity, for example. It's not always the case, but you know, in the realm we are going to deal in this class, yes, most of the time it's a constant. So it can go out, okay? And we have the integral on E, dr, right? Li, Lf. And what I can do, I can divide by q, right? It's a constant. I can divide this and this. And what I'm going to get if I'm going to divide by q, let's put it here and divide by q. This minus is going to stay, but I'm going to have w divided by q equal to uf divided by q minus yi divided by q. You see it? This term called differential voltage. Some change in voltage. This is potential at the final place, and this is potential in initial place. Okay? This is the definition. Okay? And now I want to talk a little bit about it. Okay? So in physics 1, okay, I'm going a little bit here. In physics 1, what was only the thing that was interesting? H. I'm here. Let's meter. Okay? I'm here. I have more energy since I'm at that height. Because that's the only thing that matters. And the same thing we have with the mass. We can pull out the mass of the integral. So we pull out Q of the integral. But we start with E. In this example of physics 1, G. Right? We start with E. E cannot go outside of the integral. Because most of the time, actually, camera,
It's good.
most of the time is a function of the distance, right? Of course, also in physics 1, if you're going out of space, right? And between stars and the moon and you're moving around, yes, G gonna be different. And you get superposition of all the stars, agree. No worries about it. But in electrical, in physics 2, we first see that the electric field is actually a problematic and you should stay in the integral. So to all these terms, this is what's interesting. Because the charge is not changing usually, okay? For example, let's give an example from life. If you go to China and you climb a lot of stairs, you don't say, well, dude, I'm so exhausted, I did 300 jobs today. What are you talking about? The only thing that interests us is the height. What's the difference in the height? So I did 300 stairs, right? Because stairs is a unit of height, it's dy. This is a stair. So in electric field, when we're talking about physics 2, we're actually talking about potential. What's interesting is not how much charge do you have. Like in physics 1, I don't care how much mass we're talking about. This is individual. Everybody knows his mass, everybody knows it's the gravity of Earth. I know what you're talking about when you talked about height. In electrical phenomena, we're talking about potential, which means how much did you fight the electric field. That's what's interesting, right? It was enormous electric field. You need to take your charge and push it. You know, your own charge. Everybody has its own mass. I have in my experiment my own charge. Okay, I can think in my terms. Okay, you need to fight this direction to go through the electric field. Okay, think about the wind, crazy wind, and I tried, or it was really easy, or maybe it was pushing me, right? Both of the examples are right. So this is actually the term. Let's do an example using this term with this intuition in mind, okay? So what is actually the electric field here? Okay? This one. What is, not the electric field, sorry, the potential at space. Okay, for example, let's ask what is the potential at this point. For example, at the point, forget about this cube, let's do a new drawing. So get rid of all the non-relevant stuff. So we have this problem. We have the axis. Okay, this is y, this is x, and we have here some charge q at the origin 0, 0. And I ask you, what is the potential energy of this point? 2, 2. That's what I ask you. What is the potential? What is the potential at 2, 2? When it's given, notice, when it's given, it is given that the potential at infinity equals 0.
Okay.
What did I just say? What is when the potential in infinity is equal to 0?
What is the symbol being used for
Phi.
potential?
Phi. Phi. Okay?
The R reference is 0.
Huh?
The R reference.
Exactly what I said, the reference. Remember in physics 1 what we did? We had the reference that the ground, the sea level, usually is 0. The same thing happened in physics 2, but a better reference is going to be infinity. Why? Notice. If I'm going to put, R initial, yes, to be infinity, so what's going to happen to this term? Think about it. If you're going to go far away from the particle, what is the energy that I feel here? I feel the charge. I feel it's pushing me. I feel some energy. If we're going to go that, less energy, right? Because I'm far away. Coulomb's law, remember? The force is proportional to the distance squared, right? And if I'm going to go to infinity, I don't feel it at all. I'm free to move. Nobody going to push me, nobody going to stop me, nobody going to pull me, right? So the energy there is free, which means the energy there is 0. So this is what usually happens. It's not all the cases. We're going to do another exercises in the videos, the next videos, when it's not the case, but it's the convention to have the reference point of infinity, and then you can say that phi at some location, equal minus 0, yes, cancel out minus 0, is from infinity to our final. E vector minus here, dr. And I want to remind you that we have this minus negative where it's coming from, because it was the opposite of fighting the electric field. That's what happened. So you got minus. That's the reason it's here. Okay? So now we know how to calculate the potential with some reference point. Okay? So what is actually the force? What is actually not the force, the potential energy at this location? Let's calculate it. It's really easy. So we know that phi, let's do it on this board, because here we did the energy. So I want you to notice that we don't talk here about energy, okay? We talk about potential. But potential and energy are the same. It's just a correction of the charge. It's make it not personal. That's the idea. Take any charge that you want, that's the idea, okay? So what is the potential at phi 2 and 2? it's equal to the integral from infinity to 2 and 2. E, the electric field, which we know it, right? Guys, by the way, don't forget the minus, okay? Don't break my heart, okay? See somebody do the exam, you know it's a multiple choice question, answer with minus, without minus, break my heart, okay? Be careful with that, okay? Always take care of the minus, okay? Also follow me, see if I'm forgetting the minus, we're gonna end up somewhere else, okay? So this is it's really easy subject, electric potential, really easy, and the only hard thing that I want you to notice is this minus, okay? So, what is the electric field? We know it, right?
KQ.
K, right. Q, which Q?
There's only one Q.
But if I had a charge, we normalize it, we divide it by this charge, right? It's actually Q, right? This one, that produces the electric field, right? I agree that we have here some charge that we're taking with us, we want to solve the problem, but it's not there anymore, okay? It's Q applied at this point. KQ divided by R squared, right? dr, right? This is the problem. So KQ can go outside, minus KQ, and the integral is 1 over r, right? And we have a minus, so it's become positive. And now I want you to notice something. 2, this is of course the distance, right? I want you to notice something, okay? What's going to happen? I know it looks scary to put infinity. What's going to happen? Look.
0.
KQ divided by this, which is 2 squared plus 2 squared, square root, right? Minus something enormous, really far away. What's going to happen to this term?
0.
It's going to be 0. Why? Because this is nothing compared to that, to the infinity. So actually, I know that in physics 1 it was nice to say 0, it's high 0, but in physics 2 we actually want to talk about infinity. We saw that also in Gauss's law. When we have infinity wire, stuff becomes easier, okay? When we do potential in infinity, stuff becomes easier. So infinity, compared to the physics 1, is not that frightening anymore. Infinity is a good thing in physics 2. Okay, so you want to encourage infinity in your calculation. You want to find infinity in general. Okay, so this one is 2 squared 2 KQ. And what is this one? Is the potential energy and this location, right? If I want to get the energy, not the potential energy, the only difference is to multiply it by my Q. Right? This is the energy at that location to bring that charge. Right? Understood? So this is actually what's standing between potential energy and the real energy, okay? But again, this is not that interesting. It's not interesting. What's really interesting is that. That's more interesting. This is more intuitive. Like say, I climbed today 200 stairs. It's the equivalent to say, dude, I put in my device 200 volts. That's the equivalent, okay? This is more intuitive as an engineer, and we're going to talk about startups, about cool ideas, about your own ideas, and you're always going to find yourself want to deal with potential. Like you have a battery, you don't say this is 300, no. You said this is 9 volts, right? Battery. The microphone that we're using right now is a 9 volt battery. Okay? What?
You scared me. I thought you were going to say that the microphone was...
No. The microphone, I hope is
No, it is.
It's on. Perfect. Okay. So, let's move on. So, now why I deleted us? So, never mind, I'm going to draw it again. So, let's make this question more of a more challenging, okay? So, if I have here charge Q, and I still want to know what is the potential at this point, but I'm going to do something nasty. I'm going to say, okay, let's put at this location charge minus 2Q, right? And at the location minus 2, and also 3Q charge at this location, which is plus 3 minus 3, okay? Easy to remember, 3, 2, yes? Now what's going to happen to the potential? Notice. This one want to push me.
Superposition.
This one want to push me. And this, yes, exactly, it's a superposition. Do I allow to do superposition electric potential?
Yeah,
Yes.
Why can I do it?
because it depends on the
Yes, electric field is actually what?
super.
It's superposition. And you put electric field inside an integral, it's a superposition, it's okay. It's a linear, no problem. So what we actually need to do is to find what is the potential. This is the question. The question is to what is the this is still helpful. This is the question. What is the potential at point 2, 2? And I know using the superposition, right, that is equal to phi from charge 1, let's call it charge 1, plus phi plus minus a plus t and 3. That's what we need, right?
Yeah.
That's all. We found that one already. Yes, it was kq and divided by 2 square 2. We found it, right? And it was positive, right? What is this charge?
Just do the integral.
It's to do the same thing, okay? It's to do the integral, but I can already save your time and say that this is actually k. It's going to be the same term, but the only difference is going to be here.
2 is gonna cancel.
It's the only difference is going to be, sorry, I have here 2q minus 2q. This one right now produces the electric field, right? But I have here that it's not in the center, right? It's moved to the side. So what is the full equation? The full equation is putting here the point of interest, right? Where I want to find it, and which in our case is what?
2, 2.
2, 2. And here is who produced the electric
Negative
field.
2.
Okay, who is the origin?
Negative 2, 2.
So it's negative 2, 2.
Okay, so we're not integrating
No,
to
it's
infinity.
in the negative 2 and positive 2, right?
Positive 2.
No, so the difference is that you don't calculate using the reference as infinity in this case because you have 2 charges already.
I still gonna use infinity.
In this one,
Yeah, this
Yeah.
one, the same thing. Because this one gonna be
okay,
infinity
so you are-
minus
okay,
the
okay.
small stuff, so
Mhm.
it's again gonna be the same. But I need to generalize it and put it that my origin is actually big.
Okay.
So this is correction and plus. And look, what is gonna be the potential energy? What sign? Minus, negative. It's gonna pull me toward if I come with the charge, right? That's the idea. It's gonna be a free energy. It's like falling from a mountain. Okay? It's like jumping. It's gonna be a negative energy. Okay? And the last term is 3q, and the same idea here is 2, 2, the point of interest minus the location of the one that produced my charge.
3, negative 3.
Okay? And it's a magnitude of this vector as we did in tutorial 2. Okay? So we're going to sum them up and get a final result. So it's going to be phi 2, 2 equal to kq, and we have here 1 over 2 square 2 plus half plus 3 by square 2. Okay? Got it? So guys, this was the introduction to electric potential. Now you are ready to continue to the next video. I'm going to put it here in this square. And so the next of the tutorials you're going to deal with superposition, with rings, with the case when the reference is not that clear, not at the infinity 0, what is not usually happens, so you can see to have other perspective. And this is a super interesting subject. And that's it, guys. Good luck with the homework. Thank you for staying. Thanks for Ben to recording this tutorial. And also, I forgot your name?
My name is Shubhankar.
Shubhankar. Okay, I need to earn to remember this name. Okay, guys. Thank you so much for the people in Zoom. Bye-bye.
But